This is the 8th video in a series devoted to complex analysis. In our previous video, we looked at continuity and differentiability of complex valued functions. And now we want to further that by looking at the notion of an analytic function and prove a nice test for deciding whether a function is analytic or not. So let's start with the definition. So a function f is said to be analytic on an open set U, which is a subset of complex numbers, if it is complex differentiable at every z in U and the derivative is continuous. So this is essentially just complex differentiability with this added restriction of the derivative being continuous, which actually comes from for free in this case. And we'll see exactly why that is in a bit. But before we do that, I'd like to prove a proposition. So let's suppose that f is analytic on a path-connected domain D, which is a subset of complex numbers, and define a new function g of z to be the conjugate of f evaluated at z conjugate. So we're conjugating two times here, one in the inside of the function and one on the outside of the function. Then we'll define d star to be all z bar, where z comes from D. So this is actually a reflection of the set D, which we looked at the beginning of the class, exactly the geometry of z bar. Then the result is that g of z is analytic on d star. Okay, so let's see how this goes. So let's take any z from d star and look at the limit that will define the derivative. So let's write this. So, and we'll consider, so I'll just start by saying g prime of z, although the understanding is that this does not exist unless the limit via the limit definition exists. Okay, so we want to take our limit as, I'll say delta z is approaching 0 of g of z plus delta z minus g of z over delta z. So this is a slightly different version of the derivative or the limit definition of the derivative than we had in the last video, but this is equivalent. But now let's use the definition of g as the conjugate of f evaluated at z bar. So that's going to give us this limit as delta z is approaching 0 of f evaluated at z plus delta z bar over each one, and then a bar over the whole thing, minus f evaluated at z bar and a bar over the whole thing. And then this is all over delta z, like that. And then the next thing that we'd like to do is maybe pull this bar, which is in this difference, over the entire thing. And we can do that if we include a conjugation down here. So that's going to give us the limit as delta z goes to 0 of f of z bar plus delta z bar, and then minus f of z bar over delta z bar, and then, like I said, a bar over the entire thing. So we're kind of distributing out the conjugation. Now notice if we were to distribute in the conjugation again by linearity and multiplicativity, we would get a f bar here, an f bar here, and then we would have delta z bar bar, which is just delta z. Now furthermore, if delta z is approaching 0, then delta z bar is also approaching 0, so I can put a bar over this. But now, if z is in d star, then z bar is in d by the definition of d star up here. So that means this limit, which is within the conjugate, most definitely exists because f is analytic on d. And so that gives us f prime evaluated at z bar bar, where the f prime evaluated at z is the limit and the bar is happening outside of everything. Okay, so there's like a lot of ins and outs of the conjugation here, but this is essentially the idea of getting from g prime of z to f prime of z bar bar. So that takes care of the differentiability, but now we have to show that this is also continuous. But that actually comes for free because since f is analytic, f prime is continuous, but the conjugate of a continuous function is also continuous, so we're good to go there. So that actually finishes this proof. Okay, so let's get rid of this and then we'll pose kind of our major goal for the video. So now that we've proven a nice warm-up result for the video, I'd like to propose the problem which will take us through kind of our big goal for the video. And that problem goes like this. So we have a good feel for the differentiability of real functions. And so that feel or intuition comes from all of the calculus classes that we've probably taken up to this point, as well as taking probably a real analysis course. So the question is, can we develop a tool to quickly test if a complex function is analytic? And that tool should be based off of our kind of knowledge of differentiability of real valued functions. And kind of as a motivation for this goal is the fact, which we proved in the last video, that the function that takes z to z bar is not analytic. And so this seems like it should be a very nicely defined function, but it is not analytic. So let's maybe get working towards this goal. So we're going to start by setting a function f of z into something involving its real and imaginary parts. So I'll write this as u of z plus I times v of z, where we have u and v go from complex numbers to real numbers. So their input is a complex number and their output is a real number. But now we can change our view a little bit and would like to change our view of u and v so that instead of going from complex numbers to real numbers, they go from R2, in other words, like two-dimensional real numbers to real numbers. So like I said, we're going to change our view so that u and v go from R2 to R. They are multivariable real valued functions with real inputs. So that means we would write something like u is equal to uxy and v is equal to vxy. And now maybe we can use some machinery of multivariable calculus here. Okay, so now that we've got this kind of mind shift of our view, let's look at f prime of z. So let's assume that f is analytic and see where this takes us. So let's notice that we can rewrite this as the limit as delta z goes to 0 of f of z plus delta z minus f of z over delta z. And since we're assuming that f is analytic, this kind of thing should exist for all paths that delta z can take towards 0. And that's kind of born out of the definition of a limit where all that's happening is you're kind of within this little neighborhood of 0. So that being said, we can look at a couple of different paths as delta z goes to 0. So the first path that we'll look at is what happens if we're coming in along a horizontal axis. So in other words, we'll take delta z and set it equal to delta x. What happens here? So now we're going to have f prime of z is equal to the limit as delta x goes to 0 of, well, this stuff up here with just delta x instead of delta z, but that's not super interesting. Let's use the fact that we have f of x decomposed into real and imaginary parts, and those real and imaginary parts are like two variable real valued functions. So that gives us something like this. So we have u of x plus delta x, and then y plus I vx plus delta x y. So observe that that is just f of z plus delta z in this case. And then we have to subtract u of xy plus I times v of xy. Great, and then this is all over delta x. So let's maybe combine real parts and imaginary parts to see what we get. So that's going to give us something like this. We've got the limit as delta x approaches 0, and then we'll have u of x plus delta x comma y minus u of xy over delta x. And then we'll have plus I times, let's see what it'll be, v of x plus delta x y minus v of xy, and then this is again over delta x. So we've got something that looks like that. But now, since this limit exists, now assuming that these functions are nice, we've got names for these two difference quotients as this delta x goes to 0. This is in fact the partial derivative of u with respect to x, and the other one is this partial derivative of v with respect to y. So we get that this is the partial of u with respect to x, and then plus I partial of v with respect to y. Now, there's a couple of different notations for partial derivatives. There's this one, and then there's another kind of shorthand that I like to use sometimes, which is this u underscore x evaluated at xy plus I v underscore x evaluated at xy. So let's maybe bring this fact up, and then we'll look at another value for delta. So we just finished showing that if f is analytic, and it has a real part and imaginary part, u and v respectively, then f prime was in fact equal to the partial of u with respect to x plus I times the partial of v with respect to x. There was a bit of a typo on the last board that said partial v with respect to y in one instance, but not the other, but this is the correction here. And so let's just recall, as we had on the last board, that can also be denoted by u underscore x, that's the partial of u with respect to x, plus I v underscore x, that's the partial with respect to x. So now that we've done this path as delta z is equal to delta x, in other words, kind of along a horizontal line, we'll do along a vertical line. And so that means we'll need delta z not equal to delta y, but equal to I times delta y. Again, that's how we go along a vertical line, keeping in mind that we're in the complex numbers here. Now we're going to play the same game. So we have f prime of z is equal to the limit as delta y approaches 0 of, well, let's see what we'll have. I'll skip maybe one of the intermediate steps, but we'll have something like this. U of x comma y plus delta y minus u of xy over I times delta y. So that's what we'll get from combining the u parts. And then likewise, we'll have I times v of x and then y plus delta y minus v of xy. And then this is all over I times delta y. That's what we'll have from combining all of the v parts. So now I want to do some simplifications. We can take this I, cancel it with this I right here. And then we can move this I from the denominator to the numerator by changing its sign. So that's because 1 over I is equal to minus I, as we saw in one of the earlier videos. But now let's notice that that is the partial of v with respect to y, that's the real part, minus I times the partial of u with respect to y. That's the imaginary part. So the real and imaginary parts have kind of switched here. Now, if you wanted to use this other notation, we would see that this is v underscore y minus I times u underscore y. So now let's bring this fact up, and then we'll see what we have. So we just came up with a nice result. If f was analytic, we could calculate its derivative along two paths, and we got two different versions for its derivative. On the one hand, it was the partial of u with respect to x plus I times the partial of v with respect to x, but on the other hand, it was the partial of v with respect to y minus I partial u with respect to y. But like I said, these two need to be the same in order for f to be analytic. But since this is broken up into real and imaginary parts, that gives us two equations, one equation for the real parts of each equation, or of each of these, and one from the imaginary parts of each of these. And those equations are known as the Cauchy-Riemann equations. So notice we have partial u partial x is equal to partial v partial y. So let's write that down. Partial u partial x is equal to partial v partial y. And then by equating imaginary parts, we see that the partial of u with respect to y is equal to minus the partial of v with respect to x. So like I said, those are the Cauchy-Riemann equations. And if we assume f is analytic and it breaks into real and imaginary parts, then f must satisfy the Cauchy-Riemann equations. And in fact, if f satisfies the Cauchy-Riemann equations, then it's also analytic. And we'll prove that in the next theorem. So now we're ready for maybe our most important result to date in the course of these videos. And it's based on what we saw on the last board. So let's let f equal u plus iv, so it's a function, defined on a path-connected open set D, which is a subset of C, where u and v are both functions from R2 to R. Then f is analytic on D if and only if u and v have continuous first partials on D and satisfy the Cauchy-Riemann equations. So we just got done proving the forward direction as kind of our exploration. So all we need to do is prove the reverse direction. And I'd like to point out here that this turns our complex derivative equation into kind of a multivariable calculus question. So that's nice because we probably have some intuition for real valued functions. Okay, great. So let's, like I said, do this reverse direction. So let's suppose that we have f, which is equal to u plus iv, where u and v satisfy this rule right here and the Cauchy-Riemann equation. So in other words, we're assuming the right-hand side of this if and only if statement. So I'll leave off some of that stuff like continuous first partials, but I'll definitely point out that these satisfy the Cauchy-Riemann equations. So I'll just shorten that to CR equations. I think that's kind of standard. So now I'll apply a linear approximation. This is actually a Taylor's linear approximation to both u and v. So we're going to take u evaluated at x plus delta x comma y plus delta y, and we'll say that that is equal to u of xy plus the partial of u with respect to x at xy delta x plus the partial of u with respect to y at xy delta y plus a remainder r1. So a lot of times this is written as an approximate equality without the remainder, but we can throw the remainder in there and get the inequality, and that remainder satisfies a limit condition, which we'll talk about in just a second. Then we can do the same thing for v. So we've got v, x plus delta x comma y plus delta y can be rewritten similarly. So we have v of xy, and then the partial of v with respect to x, xy delta x. And then the partial of v with respect to y, xy delta y plus r2, where again, that's another remainder. And what's the rule for the remainder here? Well, the rule goes something like this. So I'll say where r1 over delta z and r2 over delta z will approach 0 as delta z approaches 0. And so that's going to be extremely helpful when we start putting this in terms of the derivative. And now I'm going to set delta z equal to delta x plus I delta y, and then put these two together so that it looks like our function f. So now we'll have something like this. F of z plus delta z will be equal to f of x comma y. So how are we getting there? We're getting there exactly by adding u plus iv. So this u plus iv will give us f z plus delta z. And then this u plus iv will give us f of xy. And then we'll similarly have things like that over there. So let's write this. So we'll have plus ux plus I vx delta x. So I've left off my xy there just kind of for shortness. And then I'll also have plus uy plus I vy delta y, and then plus r1 plus I r2, like that. So this is looking good. Let's maybe bring that up and then we'll move on towards the end of this proof. Okay, so this is what we got to on the last board. We have f of z plus delta z is f of z. And then this combination of kind of the x change and the y change. And then I group those two remainders together into one thing. Now we're ready to try to simplify this. Again, we haven't used the fact that these satisfy the Cauchy-Riemann equations, so that's probably something that we want to do. So let's notice that since these satisfy the Cauchy-Riemann equations, I can replace this uy with minus vx, and I can replace this vy with ux. So again, let's just recall that that is exactly the Cauchy-Riemann equations. Okay, so now what can we do from that? So now we've got f of z plus, we can factor a ux out of some stuff, and notice we're left with delta x plus I delta y. So we've got the delta x from this term, and then the I delta y from that term. And then let's see what happens when we factor a vx out. So we can factor a vx out, and we're left with I delta x, and then minus delta y. And then we have plus the remainder here. Okay, so this is actually looking good because notice this term right here is exactly equal to delta z, but that guy over there is not quite delta z. But luckily it is I times delta z. Recall delta z, well, it was this. If we multiply this by I, we get that thing over there exactly. But that's what we want because now we can take this I out here and then start factoring some things some more. So that's going to give us something like this. So f of z plus ux plus I vx times delta z plus our remainder. Now remember, the quotient of our remainder with delta z will tend towards 0 as delta z approaches 0. So this change right here that allowed for this factorization is why those Cauchy-Riemann equations were so important here. Now we can try to calculate f prime of z. So a priori, we don't know f prime of z exists, but I'll just write f prime of z equals the limit, and we'll show that limit exists by our linear approximation here. So that's going to give me the limit as delta z approaches 0 of f of z plus delta z minus f of z over delta z. But now I can make my replacement. Notice if I subtract this f of z over to this other side of the equation, I'm left with all of this stuff. So now I can rewrite that as the limit as delta z goes to 0 of u sub x. Notice the delta z over delta z cancels out, plus I v sub x. Notice again, the delta z over delta z cancels out, plus our remainder over delta z. But remember that remainder by Taylor's theorem, or the linear approximation, will approach 0. So we're left with the partial of u with respect to x plus I times the partial of v with respect to x. But because u and v have continuous first partials, we know that this object down here, well, most definitely exists and is continuous, but that's what we needed for f to be analytic. So now we've got a really nice concrete test for when a complex valued function is analytic. Let's look at some examples. So I've left the Cauchy-Riemann equations on the board because they're going to be important for our examples. So let's check some standard complex valued functions are indeed analytic or not analytic as is appropriate. So for our first example, let's look at the function f of z equals z squared. But throughout, we'll write z as x plus iy. So that means this is x plus I times y squared, which means we have x squared minus y squared plus, let's see, I times 2xy. So in the language of the Cauchy-Riemann equations, we have our function u is equal to x squared minus y squared, and our function v is equal to 2xy. Now let's just check that the Cauchy-Riemann equations are satisfied. Although we did check this was analytic using the definition of the derivative on the previous video. But I think it's nice to recheck using the Cauchy-Riemann equations. Okay, so let's notice the partial of u with respect to x is 2x, but that's definitely the same thing as the partial of v with respect to y. And then furthermore, the partial of u with respect to y is minus 2y, but again, that is minus the partial of v with respect to x. So yes, that means f of z equals z squared is analytic by our previous theorem. Okay, nice. So now let's look at another example. This example we showed was not analytic in a previous video, but again, we're going to check it. So let's take f of z to be equal to z bar. So that's going to be x minus iy, the complex conjugate. But that means that we have u is equal to the function x, and v is equal to the function minus y. But notice that the derivative of u with respect to x is 1. That's not equal to minus 1, which is equal to the derivative of v with respect to y. So that's why this thing is not analytic. It does not satisfy the Cauchy-Riemann equations. So let's look at another one. Let's look at maybe an exponential function. So if anything is right with the world, that should be nice and well defined, and it should probably be analytic. So let's take f of z to be equal to e to the z. We need to decompose that into real and imaginary parts. We can do that by writing this as e to the x times e to the iy, which is e to the x times cos x plus I times e to the x, sorry, that should be cosine y times sine y. Okay, great. That's using kind of Euler's decomposition or Euler's formula for a complex exponential. So that means this is our function u, and this is our function v in this setting. So now let's take the partial of u with respect to x. It's pretty easy to see that that is e to the x cosine y, because the derivative of e to the x is e to the x. But that's going to be the same thing as the partial of v with respect to y, given the derivative of sine is cosine. Then if we look at this, so if we take the derivative of u with respect to y, so derivative of cosine is minus sine, that gives us minus e to the x sine y, which is definitely minus the derivative of v with respect to x, kind of for the same reason the derivative of e to the x is e to the x. So that means this exponential function is indeed analytic. So let's clean up the board and we'll look at a couple more examples. So we looked at the plain exponential function on the last board. Now we're going to look at a souped up version of it. So that's e to the alpha x, where alpha is any complex number. So it follows this is analytic just from the chain rule and composition of functions, but let's do it by hand just because it's a nice practice. So maybe we'll set alpha equal to a plus b times I. So that means here we have e to the a plus bi times x plus iy, given that z is x plus iy. But now we can multiply this out. I guess without saying, we should say that a and b are real numbers. So it's the real and imaginary part of alpha. So let's see. That gives us e to the ax minus by plus I times, let's see, we'll have bx plus ay. Or maybe we'll write that as ay plus bx. But now using Euler's formula, that can be rewritten as e to the ax minus by times cosine of ay plus bx, and then plus I e to the ax minus by times sine of ay plus bx. Great. And now let's check the Cauchy-Riemann equations. So notice that this guy right here would be our function u. This guy right here would be our function v. So let's take u with respect to x, the derivative of u with respect to x. So let's see, we'll get an a from taking the derivative of this, keeping in mind that we have to use both the chain rule and the product rule. So we'll have a e to the ax minus by times cos ay plus bx. So that's taking the derivative of the exponential, holding the trigonometric part constant. And then we'll have minus b times e to the ax minus by sine ay plus bx. So that's taking the derivative of cosine, which is minus sine. We get the b out because we're taking the derivative with respect to x. Now let's take the derivative of v with respect to y and make sure we get the same thing. So let's see, a minus b will come down here. So that's going to give us minus b e to the ax minus by times sine of ay plus bx. Now we have to take the derivative of this guy with respect to y. Derivative of sine is cosine, and the a comes out because of the chain rule. That'll give us plus a e to the ax minus by times cosine of ay plus bx. But notice it all worked out perfectly, and we indeed do get ux equals vy. I'll let you guys check the other one. It's really just kind of the same kind of thing. Notice this is a little bit more powerful than you might think it is, because all the trigonometric functions can be defined in terms of the exponential functions. So let's notice this implies sine z, cos z, tan z, etc. are all analytic. Obviously analytic in their kind of appropriate domains, because these are discontinuous in some places. You can't evaluate tangent at like pi over 2, for instance. For instance, cosine of z is equal to 1/2 e to the iz plus e to the minus iz. And then e to the iz and e to the minus iz are analytic from what we just checked right here. And then kind of nominally, the sum of analytic functions is also analytic. So we're good to go. Cosine of z is analytic. And then similarly, so is sine of z, tangent z. Like I said, all of the standard trig functions. So let's get rid of this. We've got 2 little results to prove, and then I'll leave you guys with some warm-up exercises. Now we're going to end with 2 pretty simple results. So they both have the same hypothesis, or the same setup. That is, f is analytic on a path connected domain D, which is a subset of C. The first result says that if f prime of z equals 0 for all z in D, then f of z is indeed constant. So this is well known for real valued functions. So indeed, it also works for complex valued functions. Okay, so let's see how we can do that. So let's suppose that f of z equals u plus iv. Since it's analytic, it satisfies the Cauchy-Riemann equations. So that means we have ux equals vy and uy equals minus vx. But also we know f prime of z equals 0 and is equal to ux plus ivx. Again, by previously, we know that the derivative is equivalent to this. But this guy right here tells us that ux equals vx equals 0, because the whole thing is 0, so the real and imaginary parts are 0. But now, this line right here, together with the Cauchy-Riemann equations, and this together with the Cauchy-Riemann equations, tells us that vy equals uy is also equal to 0. So both first partials of u and v are 0. But if both first partials of u and v are 0 from multivariable calculus, that tells us that u is equal to a constant. So I'll just say a, which is in R, and maybe v is equal to b, which is also in R. So they're both constants. But that tells us that f of z is equal to the constant a plus bi, which is complex. So that finishes the proof of number 1. Now let's move on to the proof of number 2. And that says if f of z is a real number for all z in D, then f of z is constant. So I think this is pretty interesting. This is kind of building off of one of the warm-ups that we had in the last video, that the real part function was indeed not differentiable. So let's maybe see how this might go. So here we have f of z equals u of x comma y plus, now nominally this is just I times 0. Again, because we're assuming this is always real, so the real part is the only thing that exists here. But since this is analytic, it satisfies the Cauchy-Riemann equations. That means u sub x, the derivative with respect to x of u, is equal to the derivative of v with respect to y, but that's 0. And then furthermore, the derivative of u with respect to y is equal to minus the derivative of v with respect to x, but again, that's the derivative of 0 again, which is 0. So we have ux equals uy equals 0, but that means u is equal to a constant. But if u is equal to a constant and f is only made up of u, that tells us that f is constant. And that finishes the proof of this second little result. Okay, so like I said, now I'm going to leave you guys with some warm-ups. So I'll leave you guys with 3 warm-up problems. The first is pretty simple. It was kind of similar to one that we did today, and that is show that the function f of z equals z cubed satisfies the Cauchy-Riemann equations and thus is analytic. Next, decide whether the following function is analytic. So it's e to the minus y cosine x plus I sine x. And then finally, decide when the function f of z, which is a times z squared plus b times z bar plus c times z bar squared is analytic. So it's obviously going to be analytic if b and c are both 0, because we already showed that f of z equals z squared is analytic. But is it possible to massage the values of b and c so that something like this satisfies the Cauchy-Riemann equations? And that's a good place to stop.